And we are now on to LNL section 14 titled Motion in a Central Field. On reducing the two-body problem to one of the motion of a single body, we arrive at a problem of determining the motion of a single particle in an external field such that its potential energy depends only on the distance r at some fixed point. This is called a central field. So a central field is where U depends only on R at some fixed point. The force acting on the particle is F equals negative del U del R, and its magnitude is likewise a function of R only, and its direction is everywhere that of the radius vector. So its direction would be R hat, and its magnitude is also a function of R. And as has already been shown in section 9, the angular momentum of any system relative to the center of such a field is conserved. The angular momentum of a single particle is r cross p, and since it is perpendicular to r, the constancy of the angular momentum shows that throughout the motion, the radius vector of the particle lies in the plane perpendicular to m. So m and r are perpendicular. Thus, the path of the particle in a central field lies in one plane, and they both lie in one plane. Using polar coordinates r and phi in that plane, we can write the Lagrangian as L equals 1/2 m r dot squared plus r squared phi dot squared minus u of r. This function does not involve the coordinate phi dot explicitly. Any generalized coordinate which does not appear explicitly in the Lagrangian is said to be cyclic. So if a coordinate does not appear in the Lagrangian, it is said to be cyclic. For such a coordinate, we have by Lagrange's equation that d dt of del L del Q dot is equal to del L del Q, which is also equal to 0. So that the corresponding generalized momentum is equal to del L del Q dot I. And this is also a integral of motion. This leads to a considerable simplification of the problem of integrating the equations of motion when there are cyclic coordinates. In the present case, the generalized momentum, so if we were to take the generalized momentum of the Lagrangian here, we take the derivative, the partial derivative only with respect to q dot, which would just be 1/2 mr, so q dot is only 1/2 m r squared phi dot squared, and taking the partial derivative of that, we get del L del q dot I is equal to mr squared phi dot. And this is the same as angular momentum. So we can define the angular momentum in the z direction as simply just capital M, which would also be equal to pi equals to del L del q dot I. And since we're using phi dot, we can just replace q dot with phi dot. And this would also indicate that it is equal to a constant, because upon taking the time derivative and it becomes equal to 0, then that would mean that it is constant in time. Now, this law has a simple geometrical interpretation. In the plane motion of a single particle in a central field, the expression 1/2 r dot r d phi, so 1/2 r dot r d phi, is an area of the sector bounded by two neighboring radius vectors and an element of the path. If we call this area element df, then we can write the angular momentum as, so we have 1/2 r squared phi dot, and this term is simply just 2 times the momentum times the mass. So it would be 2m f dot, and I will define f dot as 1/2 r squared phi dot, this term right here. So if we multiply that by twice the mass, then we just get our angular momentum. So thus we can also express m, the angular momentum, as 2mf dot. And f dot here we will also define as the sectorial velocity. Hence, the conservation of angular momentum implies the constancy of the sectorial velocity. In equal times, the radius vector of the particle sweeps out equal areas, and this is also known as Kepler's second law. The complete solution of the problem of a motion of a particle in a central field is most simply obtained by starting from the laws of conservation of energy and angular momentum. Without writing out the equations of motions themselves, expressing phi dot in terms of the angular momentum and substituting in the expression for energy, we obtain, so if we start off by the energy is equal to 1/2 m r dot squared plus r squared phi dot squared plus u of r. And this would be, so if we rearrange for phi dot from 2mf, so m, I'll label this as big M equals 2mf equals mr squared phi dot. We can arrange for phi dot from here. So thus, phi dot will just be equal to big M over mr squared. Squaring them both, we get that phi dot squared is equal to big M squared over m squared r4. And plugging this into our equation for energy, we get that the total energy is now equal to 1/2 m r dot squared plus r squared, and replacing our phi dot squared for capital M squared over M squared R4. The 4 and this R squared cancel out, thus this becomes R squared plus U of R. And from here, we can simply solve for R dot. So R dot gives us square root of 2 over M times E minus U minus M squared over M squared R squared. Capital M squared over M squared R squared. All of this inside of a root. And integrating this, we get so first, to get this as a function of time, I'm actually just going to move this here. We know that R dot equals dr dt. So equals to the square root of 2 over M E minus U minus capital M squared over M squared R squared. Then from angular momentum, we know that M is equal to mr squared phi dot, and we can write this as d phi dt. So thus d phi is equal to m over mr squared, capital M over mr squared dt. So separating here the variable on the left hand side, we get that one over dt is equal to the square root of 2 over M E minus U minus capital M squared over M squared R squared. All of this being divided by dr. And if we just simply flip them, dt is equal to dr over the square root of 2 over M times E minus U minus M squared over M, capital M squared, over M squared R squared, all inside of a root. And from here, we know that dt is equal to d phi over M times mr squared. D phi over capital M times mr squared. So we get d phi over capital M times mr squared is equal to dr over the square root of 2 over m times e minus u minus capital M squared over m squared r squared. All inside of a square root. And moving our m and mr squared to the other side, we can express this as d phi equals dr over the square root of, so I should actually write m, capital M, coming from the other side, over r squared. And my m is going to be absorbed into the square root. So I would get 2 over m and my m squared coming from here, which would give me 2m e minus u minus m squared over r squared. And thus my phi would be equal to the integral of this plus some constant. Now these formulas give the general solution of the problem. The latter formula gives the relation between r and phi, and the equation of the path gives the distance r from the center as an implicit function of time. The angle phi, it should be noted, always varies monotonically with time, since since it's not, it shows that it can never change signs. So phi dot can never change signs. And that would be this equation here. So from the angular momentum being equal to mr squared phi dot, this can never be negative. And that also means that our final integral can never change sign. So this value always has to remain positive because of angular momentum. And the energy equation shows that the radial part of the motion can be regarded as taking place in one dimension in a field where the effective potential energy, so the potential energy affecting the whole motion, I will note that as the effective potential energy, is going to be equal to u of r plus m squared over 2mr squared. And this is just coming from my equation of energy right here. So the effective potential is defined as that equation there, and the quantity m squared over 2mr squared is called the centrifugal energy. So capital M squared over 2mr squared is defined as the centrifugal energy. The values of r for which the effective potential energy equals the total energy determine the limits of the motion as regards distance from the center. So when u of r plus capital M squared over 2mr squared equals the total energy, This gives us our limits of the motion. When this equation is satisfied here, when this energy equation is satisfied, the radial velocity r dot is 0. So this can also be shown by if our total energy, so we have this entire thing here approaching E, right? So our total energy is just going to be 1/2 m r squared, m r dot squared, plus the U effective, which is approaching E, right? So if I replace this for E, and I would get E minus E equals 0 equals 1/2 m r dot squared, which would indicate that r dot is approaching 0. And then that would indicate that when r dot equals 0, it is a turning point of the path where r, the radial vector as a function of time, begins to decrease instead of increasing, or vice versa. If the range in which r may vary is limited only by the condition where r is less than or equal to the minimum, the motion is infinite, and the particle comes from and returns to infinity. If the range r has two limits, the minimum and the maximum, the motion is finite and the path lies entirely within the analysis bounded by the circles r equals r max and r equals r min. So all of this is leading to an equation for our change in phi, which would be equal to 2 times the integral from r min to r max of our integrand, capital M dr over r squared divided by the square root of 2m e minus u minus m squared over r squared. The condition for the path to be closed is that this angle should be a rational fraction of 2 pi. So for the condition to be closed, a closed path, this would have to belong to a rational fraction of 2 pi, where m and n are whole integers. In that case, after n periods, the radius vector of the particle will have made m complete revolutions and will occupy its original position so that the path is closed. But such cases are exceptional, and when the form of u of r is arbitrary, the angle delta phi is not a rational fraction of 2 pi. In general, therefore, the path of a particle executing a finite motion is not closed. It passes through the minimum and maximum distances an infinity of times, and after infinite time, it covers the entire analysis between the two bounding circles. It shows a graph in the book, which I will make an attempt to draw. So it has a circle in the middle, which is your minimum radius, and it has another circle around it, which would be your maximum radius, and the path of the particle is taking a motion like this, never touching the middle, but eventually at some point it's going to cover every single path and until the whole circle is filled in. Now, the presence of centrifugal energy when m does not equal 0 becomes infinite as 1 over r squared when r approaches 0. So generally, This renders it impossible for the particle to reach the center of the field, even if the field is an attractive one. A fall of the particle to the center of the field is possible only if the potential energy tends sufficiently rapidly to negative infinity as r approaches 0. So for it to reach the actual center, our effective potential energy would have to increase rapidly to negative infinity as r approaches 0. And this is essentially the reason why uh, planets will never spiral into stars, and it's almost as if angular momentum is acting as a shield for the particle never to come out of this barrier here and never to touch the center in here. And this equation basically proves that statement, that planets will never spiral into stars and so forth. And that concludes section 14.